Welcome to Lecture 4. This is more about limits. It turns out that there's so much to talk about in this particular lecture that I'm going to have to break this up into two parts as well. The first part is the one that's a little bit easier, or will be a little bit easier for most people, except that it will involve a lot more algebra, and so that may be bad news for some people. The second part of it will be more theoretical, and it will be a bit harder for everybody, but there won't be quite as much algebra. So you can see which one you like the most. In any case, let's start by talking about some laws of limits. And the good news here is that limits behave according to certain laws that are very, very intuitive. In fact, it'd be nice if everything behaved like limits do, because limits do exactly what you expect them to do. So here's the first of them, very, very simple. Suppose you have two functions, f and g. You have two functions, and you add them together, let's say. If you add two functions together, what kind of a thing do you suppose you get? Well, take a wild guess, you get a function. So if f is a function and g is a function, you add them together, you get another function. So let's suppose that when you add these two functions together, you get this new function, which I'm going to call s for sum. So the question is, what would the limit, as x approaches some number a, what would the limit be of this function s? And how would that compare to the limit of f and the limit of g? Well, if there's any justice in the world, you would expect that the answer would be that you just take the limit of f as x gets close to a, and the limit of g as x gets close to a. Take those two limits, add them together, and that should come out to be the limit of the sum. And in fact, that is exactly what happens. If you take two functions and add them together to get a sum, the limit of the sum function can be computed by taking the limit of the two parts and adding them together, just the way you would expect. What happens if you subtract these two functions? You get a different function. I suppose I could change the name to like d of x, but I'm not going to do that. But the answer is the same kind of thing happens. So if you subtract two functions, the limit of the difference of the two functions can be computed just by taking the limit of each of the two components and subtracting them. What about if you take two functions and multiply them together? And you get some other function, let's say p of x. P stands for product. Take a wild guess. What do you think happens if you take the limit of p of x as x gets close to anything you like? Yeah, the answer is you take the limit of f, the limit of g as x approaches a, and you multiply those two together, and you get the limit of p, where p is the product of the two functions. So the limit of a product is the product of the limits. What if you were to divide the two functions f and g? Well, yeah, you get the quotient of the two limits, provided, now there's a catch, provided that this guy does not go to 0. If the bottom part of a quotient goes to 0, all bets are off. What that means is I can't tell you what the limit of the quotient is going to be. Then it just depends on other circumstances. So just keep that in mind. When you've got a quotient of two functions and the bottom goes to 0, you can't use this theorem that tells us that the limit of a quotient is the quotient of the limits. But that's not unexpected. You know that when a fraction has the bottom going to 0, it's going to be bad. So that's the catch here. But otherwise, everything behaves exactly the way you expect it to. When you add two functions together, the limit of the sum is the sum of the limits. If you subtract them, the difference can be computed by subtracting the two limits. If you multiply the limits. Divide the limits. Just about anything you can think of with limits that makes any sense is actually true. And I'm telling you now, enjoy it while you've got it, because these rules about limits do not exactly carry on into other things, as we will see in the next few weeks. When we talk about derivatives, these rules are not quite true. The rules about limits, yes, but when we move to derivatives and integrals, not quite so much. we'll have to look at that in detail. You might also be wondering, why is it that these things are true? Why do these rules hold? And we will talk about the answer to that question, even though maybe you don't care so much about it, because you will care when you find that you can't compute the derivative of a product as nicely as you can compute the limit of a product. Why is it that you can just multiply the limits together for limits and not multiply the derivatives together for derivatives? And there's an answer to that, and you need to have some sense of why that is. Anyway, that's going to happen later. We'll start on that with the second part of this lecture. For now, though, I just want to focus on these rules for limits. By the way, there are lots and lots of consequences of these rules, these laws of limits, and they're what you would expect. Like, for example, suppose you take a function and multiply it by a constant. Let's say you multiplied it by 7. What do you suppose would be the limit of that as x approaches any number whatsoever? Well, the 7, what would the limit of 7 be as x goes to a? Well, 7 is a constant, so it doesn't move around. It has a graph that's constantly 7 units above the x-axis. So what do you expect the limit of 7 to be? Well, of course, 7. So the limit of a product is the product of the limits, so the 7 just sits there while you take the limit of f of x as x approaches a. So constant multipliers just sit there and watch while you take the limit of the function part. And that's really a consequence of this limit of a product being the product of the limits. And other consequences of this are if you take a function and raise it to a power, like the 15th power, what would the limit of that be? Well, you take the limit of f of x and raise that to the 15th power. That shouldn't be much of a surprise. So there are lots and lots of things that behave like that. Now, the next part of this is not quite so abstract, not quite so theoretical. We're going to be using these properties, although I'm not going to invoke them by name, but we're going to use them with some specific examples. And most of these examples that we're going to be doing involve fractions. And the first thing that you should do whenever you have a fraction, you'll be looking at an f of x divided by a g of x. The first thing that you should do is try to ask yourself what's happening to the top and what's happening to the bottom. It's kind of a reality check that you have to do. And the thing is, there is this theorem that tells you that the limit of a quotient is the quotient of the limits, and a lot of times that's all you've got to do. Take the limit of the top, the limit of the bottom, and divide them. So like if the top went to 17 and the bottom went to negative 3, then the answer is 17 divided by negative 3. No biggie. Very, very simple. The problem comes in, of course, what happens when the denominator goes to 0? And there we can't use this theorem about the limit of a quotient anymore. Or what's worse, what happens if the top ends up going to 0 and the bottom ends up going to 0? That's most of the problems that you will be dealing with in homework and for assignments and for exams. Like 99% of the problems involve this kind of situation. And this situation is what we call bad news. And bad news always means that you have more work to do. It's going to be harder than just looking at it. You cannot tell when the top and bottom both go to 0 what's going on. Now it's worth spending some time thinking about this before we do any specific examples. It's like saying, if the numerator goes to 0, don't you expect the fraction to get small? Well, of course you do. But what happens if the denominator is going to 0? If the denominator is going to 0, that makes the fraction get bigger. And so what happens? The numerator is trying to drag the fraction to 0 by going to 0. The denominator, by going to 0, by getting small, is making the fraction get bigger. So you've got kind of a tug of war going on between the top and the bottom. The top wants to drag the fraction to 0. The bottom is trying to drag the fraction off to infinity. Who's going to win? Well, it depends. It depends on which of these two forces is stronger. So it's not easy to tell just by looking at this thing. So a lot of this course is going to be answering questions like, in this situation where the top and bottom go to 0, what do you do? How do you answer that question? And the answer is always bad news. It's going to be more work. It's not so bad if the bottom goes to 0. Let's say the bottom part of the fraction went to 0, and the top part went to something else, like 15. Then what can you say? Well, it turns out that you can say the answer. The answer is, if the bottom is going to 0, that makes the fraction get big. What's the numerator doing about it? The numerator is just merrily going off to 15. Is that going to stop the fraction from getting big when the denominator is like 0.001? 0.00001? You know, the bottom is getting smaller and smaller and smaller, which is making the whole fraction get bigger and bigger. F of x, meanwhile, is getting close to 15. Well, big deal. That doesn't do anything about keeping the fraction from becoming huge. Try something like, 14.9 divided by 0.00001. You'll see that that's a huge number. And the closer g of x gets to 0, the huger this thing gets. So if the bottom goes to 0 and the top of it does not go to 0, the answer is always going to be that the fraction is going to head off to infinity. The fraction blows up. So it's very simple in that case. If the bottom goes to 0, the top doesn't, answer is infinity. In all these other cases where the bottom does not go to 0, we can just use the theorem that tells you take the limit of the top, the limit of the bottom, divide them, and you're done. So that leaves us with the bad news case. What happens with the 0 over 0 situation? And for that, it's best to just look at a whole bunch of examples. So let's start. First example I want to do is one where you're dealing with things that aren't really that bad. It's the limit as x approaches 5 of x squared minus 6x plus 5 over x minus 5. As always, the first thing that you should do with a problem like this is do a reality check. What's happening to the top and the bottom as x gets close to 5? Well, the bottom is easy. You can see that as x gets close to 5, x minus 5 is getting close to 0. So this is making the fraction want to get big. But when x gets close to 5 on the top, this part is getting close to 25. This part is getting close to minus 30. And this part is just plus 5. So 25 plus 5 is 30 minus 30. So yeah, the top part, unfortunately, is going to 0. So just by looking at this thing, it's bad news. I cannot tell you just by looking at it what's going on. However, I know that this top part is going to factor when this happens. So what I can do is rewrite this problem as the limit as x goes to 5 of the bottom I'll leave the same, but the top part I can factor. And the top part factors as x minus and x minus what? Well, I bet you it's x minus 5 and x minus 1. Try it. If you FOIL it, it's x squared minus x minus 5x, which is minus 6x plus 5. So that's factoring the numerator. Okay, now remember how when you calculate a limit of a function as x approaches 5, you don't care what happens at 5. The question, what happens when x equals 5? That is not an issue for us. So we can assume x is not equal to 5. Okay, so if I can say that x is definitely not equal to 5, then I can cancel these two guys, because that's the only bad news case for this fraction. That's the only place where the domain of this function does not exist when x is equal to 5. So knowing that x is not going to be 5, the limit doesn't care what happens at 5, I can say, well, these two guys are going to cancel. So this is really the same as the limit as x goes to 5 of x minus 1. And obviously x minus 1 is not a problem at all. When x gets close to 5, x minus 1 is doing exactly what you expect. There's no problem there. So that's one type of problem. Here's one that's the same kind of problem, except maybe some of you may not have seen this factorization before. Let's try the limit as x approaches negative 2 of x plus 2 over x cubed plus 8. Again, the reality check here is what happens as x gets close to negative 2 to the top and the bottom. The top part, when x gets close to negative 2, is obviously getting close to 0. As x gets close to negative 2, x cubed is getting close to negative 8, because cubing negative 2 would give you negative 8. So the closer x gets to negative 2, the closer x cubed gets to negative 8. So the bottom part is getting close to 0, while the top part is getting close to 0. So this is bad news. This gets close to 0 and 0. So we have work to do. And the fact is that once you know that this guy gets close to 0 and it's a polynomial, then it will factor, and x minus negative 2 will be a factor of this. So actually, x plus 2 is a divisor of x cubed plus 8. And if you've not done this before, this may not make a whole lot of sense, but I can do long division as soon as I know that x plus 2 goes into x cubed plus 8. And this is going to give me x cubed plus 2x. I'll subtract and get minus 2x, bring down the 8, divide again, x goes into minus 2x minus 2 times. So I'm going to get minus 2x minus 4, and this leaves me with 12. I think I did something wrong. Yes, I did something wrong. X squared times x plus 2 is x cubed plus 2x squared. So I'm bringing down this, I'm subtracting the minus 2x squared, so this is minus 2x squared plus 8. So in fact this is not right. Minus x goes into minus 2x squared minus 2x times. So this is minus 2x squared, I still have the plus 8, and minus 2x times 2 is minus 4x. So this is not 12, but it's minus 4x, sorry, plus 4x, because it's minus all of that. Bring down the 8, plus 8, and now if I'm really doing it right, then x will go into this 4 times. 4 times x is 4x, and 4 times 2 is 8, and that leaves me a remainder of 0. So in fact, x squared minus 2x plus 4 is the quotient, and the divisor is x plus 2, and that is actually going to come out to be exactly x cubed plus 8. X cubed plus 8 factors as this. Now this is a very hard problem just because of the algebra that's involved. So if it's really bothering you, don't worry too much about it. You really should know how to do this from previous algebra, but we'll go through this again. Actually, you'll go through some of this stuff again in Calc 2. But for now, just trust me on this, or go through the calculations. FOIL this out and see that everything cancels except x cubed and 8 when you're finally done. So what this is saying is that since x is not allowed to be negative 2 when we take a limit, then the limit as x goes to negative 2 of this quotient is the same as the limit of the fraction x plus 2 divided by x squared minus 2x plus 4 times x plus 2, and allowing us to cancel the x plus 2's. Which leaves us with the limit as x goes to negative 2 of 1 over x squared minus 2x plus 4, which might look nasty until you do your reality check. What happens as x gets close to negative 2 here? This part gets close to 1 over negative 2 squared, that's 4. Minus 2 times negative 2, that was going to be plus 4. And plus another 4, that's 4, 8, 12. So actually this limit turns out to be 1 over 12. Surprise, surprise. Okay, that was a reasonably hard problem which we probably aren't going to have to worry too much about. But let me show you one that you kind of do have to worry about, and unfortunately, and it may involve some more algebra that you're not going to like, but it's important. Let's do this problem. What's the limit as h goes to 0? Changing variables on you. That's not important, but you need to be able to deal with that. What is the limit as h goes to 0 of the square root of 9 plus h minus 3 divided by h? Now, before we do this problem, let's talk about some things that are dead wrong. Square roots do not distribute over addition, so don't do square root of 9 plus square root of h. That is a crucifiable offense, so don't go there. You're kind of stuck with this square root of 9 plus h. Okay, so do your reality check. What's going on here as h goes to 0? Obviously the bottom is going to 0. As h goes to 0, the bottom is going to 0. Okay, so what about the top? as h goes to 0, what happens to 9 plus h? Well, if h is getting small, 9 plus h is getting close to 9. Then what happens to the square root of that? Well, the square root of that is getting close to 3. So the numerator is going to be getting close to 3 minus 3, which is 0. So yes, this is bad news. The top is going to 0, and the bottom is going to 0. So what do we do about it? Well, you can't factor this. And so we need another trick. And the trick, believe it or not, is one that some high school people will just shudder at. Because what we're going to do in this problem is rationalize the numerator. Oh no, you're supposed to only rationalize the denominator. Well, no, not true. You rationalize whatever it takes. And in this problem, I need to rationalize the numerator. So to do that, I'm going to multiply by 1 in a clever way. I'm going to multiply this fraction by the square root of 9 plus h plus 3. And divide it by the square root of 9 plus h plus 3. Now step back and look at this and first convince yourself that I have not changed the problem. I'm multiplying by what we call the conjugate of that. This minus this, the conjugate of it is this plus that. So I'm multiplying top and bottom by that thing, which might seem to you like a horrible thing to do. Why would anybody in his right mind do something like this? Well, there's a very good reason for it. Let me show you, just on another sheet of paper, one that I used already, so that I don't have to mess this one up. Here's the idea. If you have an a minus b, which is what I'm dealing with here, just looking at it, sort of stripping away all the garbage, this is an a and this is a b, and I'm subtracting them. What if I multiply that by a plus b? What's going to happen? Well, you've all seen this before. A minus b times a plus b turns out to be a squared minus b squared. If you don't know that, stop the video right now and multiply this out and verify. But this is the difference of two squares, and it factors as the first minus the second times the first plus the second. So you're multiplying these two things together. This comes up a million times. You've got to know this backwards and forwards. But I'm using it now this way because when I multiply an a minus b times an a plus b, I'm going to be multiplying that radical by itself in this. In other words, I'm squaring the radical and squaring the second term, and the radical is going to go away. That's the whole point. That's why it's called rationalizing, because I'm making a rational quantity out of the numerator. It's not going to have any more radicals in it. The denominator is going to have radicals. Oh well, that's going to be the cost. You don't get anything for nothing. So, when you multiply this all out, here's what you get. The limit as h goes to 0. The top part, remember, becomes a squared minus b squared. So it's the square root of 9 plus h squared. Well, that just means the 9 plus h radical is gone, and it just becomes 9 plus h. And then you're going to get minus 3 squared. That's the top. The bottom, unfortunately, is going to be ugly. It's h times the square root of 9 plus h plus 3. All right, check that out for yourself. That's how you multiply fractions. You can FOIL the top if you want, but you're going to get this when you do it. And we should simplify one more time. This is the limit as h goes to 0 of, and notice that the 9 and minus 3 squared are going to cancel, and you're left with h over h times that mess. And of course the h's are going to cancel, leaving you with the limit as h goes to 0 of 1 over the square root of 9 plus h plus 3. And now, magically, you notice that the numerator no longer goes to 0. In fact, neither does the denominator. As h gets close to 0, this part gets close to 9. The square root of 9 plus this is going to get close to the square root of 9, which is 3. So this is going to have a simple answer, 1 over 3 plus 3, or 1 over 6. So that is the limit of that particular problem. Okay? One more example. Well, one more example where we have to do a bunch of algebra. Let's look at another fraction where we want the limit as x goes to negative 4 of 1 over 4 plus 1 over x divided by 4 plus x. Oops, this is the limit as x goes to minus 4. So let me make sure I don't forget that. The limit as x goes to negative 4. Okay, reality check. What's going on in this fraction? As x gets close to negative 4, should be obvious by now that the bottom is going to 0. What about the top? As x gets close to negative 4, this part is going to be negative a fourth. This is positive a fourth. Numerator is going to 0 also. Bad news. Okay, so what do we do? Well, when I look at this, it seems like there's an obvious thing I got to do. I've got to combine those two fractions on top into one fraction. How do I add fractions? I need a common denominator. So what's the common denominator going to be? It's going to be the product of those two. So this limit on top, this limit is going to be the limit as x goes to negative 4 of this messy fraction. The bottom of it is still going to be 4 plus x. I'm not going to change that. But the top, I'm going to have to get a common denominator. So you can cross multiply if you like that. It's going to be x plus 4 divided by the product is 4x. Okay? Verify that for yourself if you haven't done this kind of thing before. Take 1/4 plus 1 over x. Make these two fractions add up. You need the common denominator, which will be 4x. You need to multiply this 1 by x, this 1 by 4, and then you're going to end up with x plus 4. And that's divided by 4x. And now you have a compound fraction, and you have to flip the bottom. What fraction on the bottom? Well, this is 4 plus x divided by 1. So now I can flip and multiply, so I get the limit as x goes to negative 4 of x plus 4 over 4x times 1 over 4 plus x. Flipping the bottom and multiplying by it. And you'll notice that x plus 4 and 4 plus x are exactly the same. So they cancel as long as x is not negative 4, which it isn't in the limit. And so I'm left with the limit as x gets close to negative 4 of 1 over 4x. And that's not a problem at all. As x gets close to negative 4, the top is 1. That doesn't even move. And the bottom is getting close to negative 4 times 4, or negative 16. So my answer is negative 1/16. That's the limit of that original problem. Okay, so that is it for algebra type examples. I have a couple more examples that we need to do which are not quite so algebraic and maybe a little bit more bothersome in a different sense. Let me introduce you to a very important function which comes up a lot in many different areas of science. It's called the greatest integer function. The greatest integer function. So before I show you what it looks, well, I guess I better show you what it looks like. The notation for it is kind of weird. The greatest integer function is written this way. It's 2 brackets and then the number. So it's 2 brackets around the number that you're taking the greatest integer of. I'll say this in words. I'm not going to write it out. You can read the description in the book, but I'll tell you what it is, and then we'll figure out what it means in lots of examples. So the greatest integer, this is hard for your brain to absorb at first, it's the largest integer. That means, like a whole number, like 7, -2, no fractional part. The largest integer that is less than or equal to the number that you give it. Okay, so let's do some examples. The largest integer that is less than or equal to the number that you give it. So suppose I give you pi. Pi, which is approximately 3.14159. Okay, what is the greatest integer in pi? The definition says this is the largest whole number that is less than or equal to pi. The biggest number, whole number, that's less than or equal to that. If you think about it a while, it should come to you that the answer to that is 3. That's the largest whole number that's less than or equal to pi. What if I asked you for the greatest integer in 5? What is the largest number that is less than or equal to 5? Well, that's pretty obvious. That's 5. That's the largest number that is less than or equal to 5. So it's not a big deal for numbers like that. Numbers like 5.01 or let's make it 5.99. What is the greatest integer in 5.99? This is the largest number that is less than or equal to 5.99. The largest whole number that is less than or equal to 5.99. And that's still 5. Okay? So that's not a big deal. That's not real hard when you're dealing with positive numbers. It's a little weird when you look at negative numbers. What happens if you're looking at minus a half? What is the largest whole number that is less than or equal to negative a half? And it turns out that the largest whole number less than or equal to negative a half is negative 1. So you have to think about that a little bit and see that that's really what's happening. Okay, there are other names for this greatest integer function, other notations for it. In computer science and in many areas of science, this is also called the floor function. The floor function. It's the idea that, in fact, the notation, instead of it being denoted with two brackets like this, you'll see it like this. It's half of a full set of brackets, the bottom half of a full set of brackets. And then there's another function called the ceiling, which would be the top half of the brackets. And if you applied that to 5.99, that would give you 6. It rounds it up, in other words. The floor function rounds it down. So sometimes you'll see this notation for the floor function or the greatest integer function. In our book, we're using the double brackets, and so that's all you'll see. But for those of you in computer science especially, you will see this a lot. Or the word floor as the name of the function. Now, what's important about this function is limits. And so this gives us lots of examples where you might ask, what's the limit as x approaches a particular number? Before I answer those questions, or even ask them, let's draw a graph of this function. So real quick, if x is any number between 0 and 1, so think of decimals, like 0.5, 0.7, then the greatest integer is all 0. So you're getting 0 all the way in here until you get to x equals 1. And the greatest integer that is less than or equal to 1 will be 1. So you have a jump going on up to there. And here, when x is 0, the largest number that is less than or equal to 0 is 0. So you have a filled in dot at 0. If you take any x that's 1 point something, like 1.1, 1.2, 1.3, until you get to 2, then the greatest integer, less than or equal to all those numbers, is 1. So you're getting a graph that looks like this. Until you get to 2. And when you get to 2, the greatest integer less than or equal to 2 jumps up again to there. So it's not too hard to see that the graph of this function is going to look like that. And then if you go into the negatives, type negative a half, for example, which we did up here, the answer is negative 1. So you're getting this kind of thing, except at 0, of course, we've already got a y value of 0, so we're there. And at negative 1, the y value is going to be negative 1. The largest integer that is less than or equal to negative 1 is negative 1. So the graph continues like this. And so you can ask all kinds of questions like, what's the limit from the left as x approaches 2 of this function? And obviously the answer is 1. The limit from the right would be 2. What's the limit of this function as x approaches 2? Well, there the answer is, since the limit from the left and the limit from the right don't agree, there is no limit. But the value of the function at 2 does exist, and it's equal to 2. Okay, so there's an example that comes up a lot. All right, we have to do a theorem here, which is an important theorem. Actually, you know what? I think I'll put this theorem off until the next lecture. So this would be a good place for us to pause and take a break. So next part of this lecture is the more theoretical part, and we'll start with the theorem.